So in this video, we'll continue with the discussion of the fundamentals of quantum mechanics, and we'll start with the statistical interpretation, which is the standard interpretation that we use today. We're going to first talk about the results of measurements, then we'll talk about expectation values, then we'll talk about continuous spectra, and finally we'll bring in an alternative view, which is the EPR paradox and the idea of realists. So, the statistical interpretation, we want to talk about what's called the generalized statistical interpretation. And this generalized statistical interpretation allows us to compute the result of any measurement which we can make physically. So we say that a measurement of any observable operator, we'll call that capital Q, and observable operators are functions of the position and momentum, on a particle in a state psi of x and t, so that's the wave function, will result in a value of one of the eigenvalues of the Hermitian operator Q, which is a function of x and IH bar minus IH bar d by dx. So if Q has a discrete spectrum of eigenfunctions called f sub n, the probability of getting a specific eigenvalue Q sub n that is associated with the eigenfunction f sub n is really simple. We take an inner product of the function that we're interested in, f sub n, with the wave function of the entire state, and take the modulus squared of that. And that should give us the modulus squared of the coefficient of psi n that is made up from f sub n. And that coefficient squared is basically a probability. So if Q has a continuous spectrum, on the other hand, f sub z, so z is now a continuous variable, the probability of getting a specific result in the range dz is just given by c of z modulus squared times dz, which is the inner product of f sub z with psi modulus squared. So the traditional interpretation that we use, that's called the statistical or Copenhagen interpretation, views that the act of making a measurement collapses the wave function into the corresponding eigenstate which is measured. So if I measure eigenstate f sub n, then that's the state in which the system remains after the measurement. So in this Copenhagen interpretation, the wave function can always be represented in terms of the eigenfunctions of a discrete spectrum. So we can write psi of x and t is equal to sum of c sub n, f sub n of x, and then there is the time dependence which we neglect generally, but it's built in terms of the energy of that state, f sub n. Where c sub n can be obtained by taking the inner product of f sub n and the original wave function psi. And that is just an integral f star n sub n of x, psi of x and t dx. For a continuous spectrum, we're going to have a similar discussion later, but it'll be slightly different. So, any measurement of the operator Q must return one of these eigenvalues of Qn, that is, eigenvalues Qn, with the probability c sub n modulus squared, and a wave function psi of x and t must be normalized so that we know that 1 is equal to psi inner product of psi with psi, and that's just the inner product of the sum of over n prime of c sub n prime f sub n prime with sum over n of c sub n f sub n. And we know what that gives us because we can take the sums and the constants out of the inner product, and so we have sum over n prime, sum over n C star sub n prime, C sub n, inner product of S sub n, F sub n prime, F sub n. And since these are eigenstates, they're normalized and they're orthogonal, then the only term which survives is when you have n prime is equal to n, because that's a Kronecker delta, delta of n prime n. And so we're left with then a sum over n of C sub n star C sub n, the n primes convert to n, and that's just the sum of C sub n modulus squared. And so this puts a constraint, normalization puts a constraint on the coefficients of this sum that it makes up psi of x and t. The expectation value of q then can be taken by taking the inner product of psi with q psi. That's easy enough to do. You have, again, your sum over n prime, C sub n prime, F sub n prime. You have q applied to this sum, which is sum over n, C sub n, F sub n. And again, we can take the sums out. We can take the q into the sum. And when you apply q to F sub n, you get the eigenvalue q sub n, which is a constant, so you can pull it out again. So you have sum of n prime, sum over n, C sub n prime star, C sub n times q sub n times the inner product of S sub n prime, F sub n. Again, this is going to be a Kronecker delta, so this just becomes the sum over n of q sub n, C sub n modulus squared. Now what this is basically is a weighted average of the eigenvalues of q. So when you measure q, you get a specific eigenvalue. When you want to know the expectation value, you have to take a weighted sum depending on the probabilities of each of the eigenstates in the sum for psi sub x and t. You can make the same argument for continuous variable position with eigenfunctions given by g sub y of x is equal to delta of x minus y. Right? So this is the continuous variable, which is position. Again, c of y is just the inner product of g with psi, but since g sub y is just delta of x minus y, when you take that into the integral, it becomes very simple. It just gives you psi of y and t, where y is a specific value of the variable x. Now, the probability of measuring the particle then in the range between y and y plus delta y is simply this modulus squared of psi of y and t dy times the width dy. We can do the same thing with momentum. Remember, c of p is equal to the eigenfunction of momentum, f sub p, inner product with psi. Well, the eigenstate of momentum is just simply 1 over square root of 2 pi h bar e to the I px over h bar. And so you put that integral with psi of x and t, integrate over dx over all space, and we get, if you recall, this function phi of p and t, which is the momentum space wave function, and it's just the Fourier transform of the position space wave function, psi of x and t. These two are related by Plancherel's theorem, which says that psi of x and t is equal to 1 over square root of 2 pi h bar, integral from minus infinity to infinity of e to the I px over h bar, phi of p and t integrated over dp, because then you get only a function in x. So that means that the probability that a measurement of momentum will yield a value between p and p plus dp is simply the wave function in momentum space, phi of p and t, modulus squared times dp. So we have the same thing for both discrete and continuous spectra, we can do the same calculations in statistical interpretation. So that's the commonly understood interpretation of quantum mechanics. There are, however, other interpretations of quantum mechanics, such as consistent histories, many worlds, and so on. But one of the most important ones that was made by people who did not believe the statistical interpretation of quantum mechanics, or that the world could behave in this statistical manner, was the one that was laid out by Einstein, Podolsky, and Rosen in their paper from 1935. So Einstein and Podolsky Rosen wrote up a paper called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And this is from Einstein, Podolsky, and Rosen in Physical Review 47 in 1935. So what did they say? Well, one of the key phrases in this paper is that if, without in any way disturbing a system, we can predict with certainty, that is, with probability equal to unity, the value of physical quantity, then there exists an element of physical reality corresponding to this physical quantity. That's a postulate that they have. So what are they saying here? It says that if we can predict with 100% probability what the value of physical quantity will be, then there must be an element of physical reality corresponding to this physical quantity. There must be something in the reality that tells you that that will be the value. So let's go through the reasoning. If psi is an eigenfunction of an operator A, and it has an expectation value lowercase a, then we can write the eigenvalue equation, A psi equals lowercase a times psi. Let's take the momentum operator, for example. P is equal to h bar over I partial with respect to x. And the eigenfunction of the momentum, which is psi e to the I p sub 0 x over h bar, where p sub 0 is the eigenvalue of this particular wave function. If I apply the operator p to psi, I get h bar over I partial with respect to x times applied to e to the I p sub 0 x over h bar. When I take that derivative, I get h bar over I times I over h bar p sub 0, and then I get my function back again, e to the I p sub 0 x over h bar. The h bar over I and the I over h bar cancel. I get p sub 0 times the wave function back. So the momentum in state psi then is real, is said to be real because we can measure it. However, if the eigenvalue equation does not hold, then A can't be said to have a particular value, because we know from the position operator Q, and in Einstein Podolsky Rosen paper, which if you look it up, they use Q and P instead of X and P. So Q is just the position operator. We know that Q operator applied to psi just gives you X e to the I p sub 0 x h bar over h bar. And that's not equal to an eigenvalue times psi. Right? So if there's an eigenfunction of the momentum operator P, then it's not an eigenfunction of the spatial operator Q. So we know that the probability of finding a system in a state between A and B is equal to the integral from A to B psi star psi dx. This is going to be the integral for this wave function as a momentum operator is equal to e to the I p sub 0 x over h bar. The complex conjugate gives you a minus sign. These cancel to give you the 1. So this is just the integral of from A to B dx. And this gives you B minus A. So the probability of finding the operator in that region is b minus a. So there's an equal probability of measuring any value of the position when you have a specific value of the momentum, right? That's the Heisenberg uncertainty principle written in a different way. So this is because the two operators don't commute, so that commutator of A and B is not equal to 0. And then that means a precise knowledge of one precludes the knowledge of the other, right? That's Heisenberg uncertainty principle. We talked about that before. So the authors conclude that there are two possibilities. One, the quantum mechanical description of reality given by the wave function is not complete because you can't localize the position. Or when the operators corresponding to two physical quantities don't commute, the two quantities cannot have simultaneous reality, right? Because you can't measure the position. So there's not a simultaneous reality of the momentum and the position. Or the other possibility is that there's something missing from this description of a quantum mechanical system. So suppose that we have two systems, system 1 and system 2, which interact over a time period from 0 to t, capital T. If we know the state of each system before t equals 0, then by using the Schrödinger equation, we can calculate the state of the combined system, 1 plus 2, at any subsequent time. Specifically, the time is greater than capital T. And we'll call that the system at that point, its wave function psi, capital psi. So now let's suppose that you have a physical quantity A, it's any operator that has some physical meaning, has eigenvalues A1, A2, A3, and so on. And eigenfunctions U1 of x1, U2 of x1, U3 of x1. That's in system 1. So the subscript here is the system, the subscript here is the eigenvalue number. Then the system-wide wave function as a function of x1 can be written as a sum, like we've talked about before, psi, capital Psi of x1, x2 is equal to the sum from n equals 1 to infinity of psi sub n of x2, u sub n of x1, where psi sub n of x2 are simply coefficients of the expansion of u sub n of x1, right? Because we want this in terms of both these variables. So u sub n only depends on system 1, so psi sub n has to be a coefficient that also depend on x2. But as far as x1 is concerned, x2 are all constants. So that's fine. They're completely different coordinate systems. Now, if you measure A and find a value A sub k, then this first system must be left in a state u sub k of x1. So this is what the statistical interpretation says, right? When I measure a system, I pick out the value, the kth value, that's what I measure, then the system must be left in this value. And therefore, the second state, because they're mixed together, must be found in a state psi sub k of x2, because that's the coefficient, which depends on x2. So by measuring x1, I also impose something on x2. I impose this particular value of this coefficient. So the combined state then, after measuring and getting an eigenvalue for this operator A of A sub k is equal to psi sub k of x2 times u sub k of x1. Now, instead of using operator A, let's imagine that we use a different expansion. That is, we expand the overall wave function in terms of an eigenfunctions of B, which is a different operator. And it's an operator that does not commute with A. So these are B1, B2, B3, and so on. And we're going to call the eigenfunctions V1, V sub 1 of x1, V sub 2 of x1, V sub 3, and so on. Okay? Again, I'm using the notation in the EPR paper here. So the same wave function that we described in terms of the U's and A's, we can describe now in terms of the v's and b's. So psi of x1, x2 is equal to the sum from s equals 1 to infinity, phi sub s of x2 times v sub s of x1. Again, these phi sub s of x2 are coefficients. Now, if we measure b and find that the eigenvalue b sub r, the value b sub r, then the combined system is going to end up in the state psi is equal to phi sub r of x1, 2 times v sub r of x1. And you see the second state then must be in this phi sub r of x2 state. All right, so the consequence of two measurements made on system 1 lead to two different values, two different states for system 2. Now imagine we've taken these two systems, we'd allow them to interact for a short amount of time, and then we want to figure out what happens when they're far enough away. So remember, t is bigger than capital T. The time is bigger than capital T. So the two states have separated. We've made a measurement in one, and we get one value of the second state, second system. And we make a different measurement with a different operator, b, and we're going to get a different value for the second state, right? So these two values depend on the measurement we've made in state 1, in system 1 rather. So, as a consequence of two different measurements made on system 1, system 2 can be left in states with two different wave functions, even when it's far away from and not interacting with system 1 any longer, because the interaction happened from 0 to capital T. The time is much after that, they do not interact anymore. So we have this connection is still there. That's called entanglement, basically. So what we can do then, what we must do is assign two different wave functions, psi sub k of x2 and phi sub r of x2 to the same reality, that is system 2 after interaction with system 1. Now, given that we've been able to do that, let's assume that these are eigenfunctions of two non-commuting operators, p and q, with eigenvalues p sub k and q sub r. By measuring either a or b in system 1, what we've done is we're able to predict with certainty and without disturbing system 2 either the value of p being p sub k or the value of q being q sub r. Now, according to the criterion for reality, the one that was mentioned on the first slide of this paper, p must be an element of reality. And in the second case, q must be an element of reality. But we were told that psi of k of x and 2 and phi of r sub r of x and 2 were shown to be part of the same reality. And what this does is it leads to a contradiction of the postulate that when operators corresponding to two physical quantities do not commute, the two quantities cannot have simultaneous reality. So by making this measurement of a or b, we know what we're going to get when we make each measurement. But if p and q don't commute, we shouldn't be able to predict each one with certainty because they don't commute. And we showed that with the momentum and the position, if you predict one, the other one cannot have a reality as well. It has indeterminate value. So this is a contradiction. And so the authors conclude in this paper that the quantum mechanical description of reality given by the wave function must not be complete, right? Because you're coming up with this system where you can find the same part of the same reality being two non-commuting, the values of two non-commuting operators. So this was the argument that Einstein, Podolsky, and Rosen made. And This was called the realist version of quantum mechanics. And if this realist version is correct, then a complete description of reality must include some additional local variables called local hidden variables, which specify the state of the system completely. So that if you have that hidden local variable, then this is no longer a contradiction because you have an additional variable that's telling you what these values are going to be. So the reason I bring this up now is that in a little bit, we're going to be talking about Bell's theorem and entangled states. I wanted to bring this in because what we're going to be talking about is purely statistical interpretation of quantum mechanics. You have to be aware that there are other interpretations, and it's a bone of contention still what interpretation is really the right one or that makes the most sense.